Today, I'm going to be talking about plotting massive datasets on your laptop and specifically using SQL engines for that. So this is a really simple and elegant solution that you can apply without having to worry about big machines or clusters. Okay, so let's get started. I'm going to skip this one since I was already introduced. So let's go to the next slide. Okay, so first, let's imagine you have a large data set, and by large, it actually depends on how big your machine is, right? But it can be somewhere between 10, 20 gigabytes. What would you do with this data set? Usually, what we do is we load this data with pandas or NumPy. Maybe we are using a Jupyter Lab, so we load the data. We are on a notebook, we load the data, we make a few transformations, and then we use matplotlib to generate some charts. Maybe we are interested in plotting some histogram or a box plot or a scatter plot. Matplotlib offers all these different plots that we can use. Now, what's the problem with this traditional approach? The problem is that since we are loading all the data into memory at once, we can start getting into memory issues pretty rapidly, especially because if we are using pandas and we make a few transformations on our data, we might be creating copies of it without us noticing. Like, depending on the operations that you apply to your data frame, you might be creating copies. So you load, let's say you load this large CSV file, and let's assume this white box is the RAM, the memory that you have available on your machine. So you create a first copy, and maybe you apply a new transformation, and you create a second copy. And then you apply another transformations, and now you have another copy. So soon you'll have multiple copies of your data in your machine. And the moment you start trying to apply more transformations or plotting this data, you may run out of memory, right? So at this point, if you start to have some memory issues, you may think, well, maybe I should bring larger machine, right? So that's kind of the first solution that you may think. If this 16 gigabyte laptop is not enough, maybe I need more memory. So maybe I can just use some EC2 machine on AWS, get a 32 gigabyte or 64 gigabyte machine, and just plot my data there. Well, that's actually a reasonable solution, but you have to get this machine, you have to pay for it. And it complicates things because now you have to get this new machine, spin up the instance, then make sure that you have your code and your data in that machine. So it creates many extra steps for you just to create this simple plot. Another solution, an even more complex solution, might be, well, I'm going to use a cluster. I'm going to use a distributed framework, distributed computing framework, and then this framework will take care of plotting my data, right? Because distributed computing frameworks make sure that you distribute the workload in many machines. So this big data set may split into multiple smaller parts, and then each part can be assigned to a separate machine. This is an even more complex solution, and it requires so many extra steps because first you have to make sure that you have a cluster available to you. You have to make sure that you have a distributed framework that can process the data in parallel. So it's too many extra steps, right? So what I'm going to propose in this talk is that you can get away with a really simple solution for moderately large data sets. And this will also depend on how large your data is and how much memory you have available. But in many cases, this is a great effective solution. So what I'm proposing here is that we can use an embedded SQL engine. So let's talk about embedded SQL engines. A SQL engine is explicitly designed to perform computations efficiently. So I'm sure you have used a SQL database before, or like a warehouse like Snowflake, Redshift, or a more traditional database like Oracle, Postgres, MySQL. All of those are optimized to perform computations efficiently, right? They manage and they come up with a plan to compute whatever you want to compute. You essentially, if you have used SQL, you know that you declare certain transformations on the data. Maybe you want to group by some column. Maybe you want to compute some statistics like percentiles, or you want to take the mean. those kinds of things. You only specify the transformations that you want to apply, and then the SQL engine figures out how to do it. And it makes sure that you don't run out of memory. So essentially, you're offloading this manipulation logic to the SQL engine, who was specifically programmed to do these computations efficiently. So they are really memory efficient. Now, of course, if you are using something like Postgres, you have to install Postgres, you have to create a database, you have to upload data into a database, and then you can start running queries on it. That's why we have these embedded SQL engines. An embedded SQL engine is a much simpler engine that you can use as an alternative, and it doesn't require any setup. You don't have to set up a server. You don't have to create a database. It's a SQL interface that allows you to perform computations in a single machine. So the two most popular embedded SQL engines are SQLite and DuckDB. So SQLite, I'm pretty sure you are running many SQLite databases without you knowing. For example, your phone, many applications on your phone run SQLite, and the data is managed in a SQLite database. SQLite is a great alternative because it comes pre-installed with Python. So if you have Python on your computer, you already have SQLite. You don't have to install any extra dependencies or anything. You can start running queries with SQL by using SQLite. DuckDB is a more recent project and is specifically designed for running analytical queries. And it stores the data in a column-based manner. And the most interesting part of this is that it can run queries directly on a CSV or Parquet files and other formats. You simply write your SQL, point to the file, the data file that you want to run queries, like a CSV file, and then you can start running any kind of analytical queries. So those two are the ones that I have experience with, and both of them are great. Of course, DuckDB is a lot more optimized for these analytical queries, but you can also use SQLite for some moderately large data sets. So here I have two code examples just so you know how it looks like in practice. With SQLite, as I mentioned before, you don't have to install any extra dependencies. It already comes pre-installed with Python. So you can start a Python session, do import SQLite tree, and then you can create a connection to a database. Then you can upload the data to your database, and there are some commands that you can use, for example, to import a CSV file into a .db file, which is the format that SQLite uses. And then you can start running queries. So you see I'm running here, I'm calling the execute method, and then I'm passing this SQL command, and then I can get the results. And SQLite is taking care of manipulating the data, transforming the data. I don't have to worry about memory because SQLite is doing that for me. Here, DuckDB is pretty similar. To get DuckDB up and running, I have to do pip install DuckDB, but it's really simple. It doesn't take much effort to get it up and running. Then I can connect to a database like this. For example, here I'm connecting to an in-memory database. So I'm telling DuckDB to store all the data and all the transform data sets that I'm going to be using in memory. Maybe because I only want these transformations, I don't want to store them on disk, I just want them temporarily. And same idea, I can start running queries on my data. Now, what's interesting about DuckDB is that I can do a select star from and then pass a CSV file. And then here I can maybe select a few columns, maybe I can group by, and DuckDB is going to take care of loading that CSV file and then do the manipulations. It's going to be a much more efficient way to load and manipulate data than if I load the entire data set with pandas and I start doing some manipulations. Okay, so now let's talk about how we can use these embedded SQL engines for plotting. And the first use case that I have is a box plot. Let's say we want to create a box plot like this, and let's focus on only the first one, just to simplify things. What do we have to do to our data set to plot this box plot? Well, we need a few statistics, right? We have the median here. We also need the 25th percentile here. We need the 75th percentile here. And we also have to define this confidence interval and the cutoff for the outliers, right? So anything that's below this cutoff will appear here, and anything above the cutoff will appear here. That's the only thing we need, actually. So once we compute those statistics, we can create the box plot. So actually, let me show you how matplotlib does that. So we are going to look at matplotlib's source code very quickly. Okay, so we are looking at matplotlib's source code here, and there's a function called boxplotstats. And as you can see in the description, it says, return a list of dictionaries of statistics used to draw a series of box and whisker plots using, and then the name of the function that you use for plotting. It takes as an argument our data. So this is a vector of numbers, and then it has a few parameters. We can ignore this just to simplify things. And then I'm not gonna go into the details. I just want you to see what's kind of the logic here. Remember that X is our data. So you're essentially doing some transformations on our data here, and we are computing some numbers here. The final dictionary is this stats dictionary. And for example, one of the stats that we need is the mean, right? So we take the mean, our data. We also need the median and the quartiles. So that's what we do here with NumPy. And we get the Q1, the median, and Q3. We also need the interquartile range, so we compute it here. Then we also compute a few extra things. And at the end of the function, we return a dictionary that contains these statistics. Now, as I mentioned before, in order for us to execute this function, and actually when we use matplotlib to create a box plot, this is the code that's running. So it loads all our data into memory to compute those statistics, and then it uses this second function called bxp. Let me open it. And this bxp takes the dictionary that we computed before, right? So we essentially, it's like a two-step process. First, we compute the stats, and then we use this bxp function that takes those statistics and then creates the plot, this plot. So now to make this more efficient and to be able to generate box plots for larger data sets, we are going to substitute the first part. So instead of calling boxplotstats, we are going to implement our own function that uses SQL and DuckDB to compute those statistics, compute the statistics, and then call the second function, bxp, to draw the plot. So that's the idea. Now, this is really like a summary of how this could look like. I have an open source implementation, and I'll show the link at the end. This is just so you know kind of how it looks like. We saw that we have to compute a few statistics. One of those statistics are percentiles, right? We need 25th percentile, the 50th percentile, which is the median, and the 75th percentile. Now, how do we do that? We can create a function that takes the connection to the database. In this case, is going to be a DuckDB database because it implements a function to obtain the percentiles. Table, I'm calling this a table, but this is really going to be a CSV file, a Parquet file, and we are going to query that file through DuckDB. The column, this is the column that we want to use as input to generate the box plot. And then the percentile. This can be 0.5, 0.25, 0.75, which are the values that we need. Then I have a template, which is a template that I use to generate these percentiles that I want to compute. If this looks familiar, I'm using Jinja to compute this. So essentially, I say render my template. So convert this SQL template into some SQL code that I can run. I pass the table or the path to the CSV file, the column, and the percentile. So once I run this line, I have a SQL query that I can run on DuckDB. That's what I do here. And this is where the magic happens, because DuckDB is taking care of loading that data, computing that percentile, returning me the result, and that's it. I don't have to worry about how much memory I need because DuckDB is doing that for me. And then I can call this function multiple times for the 25th percentile, for the median, or for the 75 percentile. And we can even make things more efficient and compute everything in a single function call. So that's the idea. Of course, we need to compute a few other statistics, but this kind of gives you a high-level idea of how the code looks like. You create some SQL, you run that SQL, you compute those statistics, and then you can use those statistics to create your plot. Now, let me show you the second use case, a histogram. Kind of the same idea, right? So we have, let's say you have a huge vector of numbers, and we want to create a histogram. What do we need to create this histogram? We only need two things for each bin. We need the size of the bin and the height, right? That's all we need. Once we compute those pairs, the size of the bin and the height, then we can plot it. And we can use the bar function for that. So you start to see a pattern here, right? In order to create a plot, we need to compute some statistics. We compute those statistics with SQL, and then we use those statistics to plot the chart. So these are just two use cases, but you can extend the same logic to others. Now, the code for the histogram is actually a lot simpler than for the box plot, because we need fewer statistics. So I can show you quickly how it looks like. And I'm going to share the full implementation so you can play with it. This is just a simplified version. So same idea here. We have a function that takes a table as an argument. And remember, this is the path to the CSV file, to the dataset that we want to use as input. The column that we want to use to generate the histogram, the number of bins, and the connection to the database. So the first thing that we have to compute is the range. So we need the maximum and the minimum for our histogram. So we need to know the maximum and the minimum in our dataset. I didn't include the implementation of this function just for to simplify things, but it's the same idea. You have you are generating some SQL that returns you the minimum and the maximum value. So you're executing this on DuckDB. You can actually run this on SQLite as well, because it also has the function to compute the minimum and the maximum. Then you compute the bin size using the range. So taking the max minus the min divided by the number of bins, you compute the bin size. Then you compute the counts, essentially the height for each bin, with this SQL code. And it's the same idea that the same logic that I showed for the box plot. You render this with the parameters. You have this template. You pass the parameters that you want. You execute that in the database. And then you retrieve all the information that you need for the plot. In this case, what you have are the bins. So essentially the start of the bin, the left side of it, and the height for each bin. And then you use matplotlib. And then you pass the bins and the height, and that's it. You generated a histogram without having to load all your data into memory. Let me go to the next slide. Okay. Now, I have an open source implementation for both of these things. So you can use it to look at the code, see it in detail, and see how the implementation looks like. And also, you can try it. So you can do pip install jupySQL, and you can find the documentation here, github.com/plumber/jupySQL. We also want to show you some quick demos so you can see how it looks like in practice. Okay. So here, what I'm doing is I am loading some data into a DuckDB database. Let me hide this for now. Yeah, so I'm loading some data here, and then I am showing some of the rows. This is some sample data set that I found that contains, I think this is a music store database, so it contains information about albums and sales and some extra information. Now, what I do here, let me come here. Yeah, right here. So I implemented this histogram function that takes the files that you want to use. In this case, my data is split across several files. So I have 12 files, Actually, this is not the record music store. I'm using a different data set. So this is the New York City. Yes, this is the New York City taxi data. And it's, I think these are, one row is a taxi trip in New York. So it's a couple million, actually we have the count here. So it's 4 million rows. So I have 3 months of data, 4.5 million rows. And what I'm doing here is I'm calling this plot histogram function that implements the same logic that I just described. And I'm saying, look at all these three files, then go to trip distance column and create 50 histogram with 50 bins, which is what you can see here. And then it generated the plot for me. Now, I cannot see much here because we have a few outliers, right? So then what I can do is I can tell DuckDB to find the 99 percentile. And it returns me 18.93. And then I can tell DuckDB to create a new data set with all the values below this cutoff value. So I can see my histogram more clearly. And then I create a new data set, and then I call my function again, plot.histogram. Now this data set doesn't contain any outliers. Trip distance, bins equals 50. And now I can see my histogram. And then I'm printing the memory usage. And you can see that I'm only using 0.3 gigabytes of memory. This is because DuckDB is loading the data, computing the statistics, and then shutting down the process. So I don't use a lot of memory. Now let me show you a benchmark. I'm going to create the same histogram, but using pandas and matplotlib. So same idea, same data set, and I'm going to call this the histogram function in matplotlib directly. And I'm loading this as a data frame. So you can see I have the same problem at the beginning, that I have a few outliers, so I cannot see much of my histogram. Then I compute my cutoff value, and then I call the histogram function again. And I get pretty much the same thing. But look how much memory I'm using. I'm using 1.2 gigabytes of memory, which is a lot more than 0.3. And this is actually not a large data set. So if we imagine what happens if we have a data set 10 times as larger as this. With DuckDB, it will remain the same, just 0.3 gigabytes of data. But with pandas, it will blow up the memory, and I probably won't be able to create this plot. Okay, so that's it for me. I have my contact information here in case you want to ask me any questions, my email, my Twitter account, my LinkedIn, and I hope you enjoy the presentation. Remember that I have this open source implementation, so you can go and look it in detail, because I have to skip some important information. But yeah, thanks a lot for watching.
Thank you very much for giving us this amazing talk. And we still have a few minutes for questions.
Mm-hmm. So I see one question. Is it possible to increase the computing speed with this method? I didn't run benchmarks for speed. My guess is that the speed would be comparable once you have the data in memory, because NumPy is really efficient. But I think it's an interesting question. So maybe depends on the size of the data. You may get some speed ups with the SQL engines, although once you have the data in memory, it's a lot faster. So it's an interesting question. I would have to run some benchmarks. I think the main benefit here is mostly memory, that DuckDB and SQLite can manage the memory for you. But yeah, I think depending on how large the data is and what types of transformations you do, you may get some speed improvements. See another question. What kind of problem are you resolving? Well, it's mostly about convenience, right? It's a simple solution because if you try to run, if you want to run this, create these plots for large data sets, you either need a big machine. So let's say you want to stick with pandas and matplotlib. You can either get a big machine or run this in a cluster. So what I'm proposing here is to use a simpler alternative, which is DuckDB or SQLite. And this is a lot simpler than getting some big, easy to instance or configuring a cluster. So it's a much more powerful way to scale the analysis using SQL. And I think this is just a use case. I'm plotting data sets, but you can extend this to many other domains. Like you don't have to create plots to use these powerful SQL engines. You can use them for manipulating your data. So for example, if you are having problems with pandas and memory, you can do everything that you can do with pandas, you can do it with DuckDB. So that's also a powerful alternative. If you are having memory issues with pandas, you can use these SQL engines and you can transform larger data sets without worrying about memory issues.